Welcome to the Genius Factory. Enjoy the video.
You start by writing the Nernst equation and converting ln to log 10 if preferred. Use the 303 factor so numbers are manageable. Next, identify the balanced half reaction and count n, the electrons transferred, because n scales the correction term. Then write Q as the product of product activities over reactant activities with powers from the equation. Once done, make sure you have concentrations or partial pressures for each species, and note whether activities approximate concentrations or require activity coefficients, since that alters log Q. You now compute Q numerically. Substitute concentrations or partial pressures into the Q expression using stoichiometric exponents. Use log rules to simplify. Take log 10, Q as the sum of each species exponent times log 10, activity, which avoids tiny or huge intermediate products. If species are gases, convert to ATM. If ionic, convert to effective activity using activity coefficients when precision matters. Once you have the summed log 10 terms, divide by n as required later in the voltage correction, keeping consistent units throughout. You finish by inserting your computed log 10 Q into the Nernst form E equals E degrees 0.05916/n log 10 Q at 25 degrees C. This yields the cell potential adjusted for non-standard conditions. Remember why the sign matters. Swapping numerator and denominator in Q flips the sign of log Q and thus the voltage correction. If your result seems wrong, troubleshoot by rechecking stoichiometric exponents, verifying concentration units and gas pressures, and testing whether using activity coefficients versus concentrations materially shifts.
Thanks for watching. If you found this helpful, don't forget to like and subscribe.